Thank you all for coming to the SOLIDWORKS Vibration from Beginning to End webinar. I'll be your host today, Sean Bentley. Got a lot to cover with you today, so let's go ahead and dive right in. So on the agenda, first thing we'll be talking about is what's inside of the SOLIDWORKS Simulation suite that'll help cover vibration. Then next we'll talk about a little bit of vibration background, some fundamentals that'll be important for me to actually distinguish between the different tools. And then we'll run some vibration examples on a pretty simple model. It's going to be this basketball hoop here, just so that it'll run quickly and we can do some quick comparisons to give you a general idea of how these tools might be used. So to start with, the SOLIDWORKS Simulation suite of tools shown here: Simulation Standard, Sim Pro, and Sim Premium. I've kind of got highlighted the core utilities inside of each package. So the ones though that we'll be focusing on this presentation though are going to be the ones that are related more to the vibration side of things. And so particularly the frequency and the dynamic studies that are available in Sim Premium. You might wonder why I have linear static included in this list. Well, we can use this tool still to help us solve for some vibration problems. All right, so next what we'll get into then is some fundamentals that are going to be important for trying to distinguish between the different functionalities available in each of these tools. So to start with, going back to this little subset here, Simulation Professional has frequency analysis. Let's talk about that first, a little bit about some fundamentals that are going to be important. So for frequency analysis, we're going to calculate something called natural frequencies, and likely many of the people who are attending this webinar might already know some things about this, but bear with me a moment and I'll just kind of clarify some terms and the way I'll use them. So what I'd like to talk about though is picture I have a meter stick, and I think we've all done this at some level, a little physical experiment of picking up a meter stick, waving it around in one hand, and seeing how it behaves. Now here's me waving the meter stick up and down. Now picture I'm actually holding it here on the left, and I'm moving it up and down at 2 hertz. That's 2 cycles a second. And is it resonating? Not really. I don't see much amplification to that. So 2 hertz is not a natural frequency of this meter stick. However, if I happen to wave it up and down more slowly at 1 hertz, I bump into resonance. Okay, so we see the natural frequency of the meter stick, one of them at least, seems to be at 1 hertz, 1 cycle a second, and the thing resonates. It responds to that frequency. Now, structures, like meter sticks, or any structure for that matter, have many resonant frequencies. Here's another one. If I were physically capable of moving this meter stick up and down at 15 hertz, that's 15 times a second, I might see this type of resonance. This almost starts to look a bit like a guitar string if you pluck it hard enough. So, and of course this resonance, it boils down to this fundamental equation here. The key parameters, I'm not going to dig into the weeds here on this, but as far as the key parameters though, the stiffness of the meter stick is important, but also masses. Picture if I put a big mass on the end of this meter stick and I try to wave it up and down, that'll have a big effect on those natural frequencies. It'll tend to lower them. More massive things will move more slowly, causing these resonant frequencies to lower. So many systems might be approximated by this type of equation. Many simple systems. Here I just have a spring mass system, the simplest dynamic system in the world, so to speak. We have here the stiffness of the spring, K, and then also the mass are the key variables in this. And this is what I'm going to use to try to calculate resonant frequencies on that on the basketball hoop that we'll be looking at later on. The basketball hoop is going to behave very similar to this system. In the case of the basketball hoop, the mass is me hanging on the end of it, and the stiffness is the bending stiffness of that hoop. And so we can actually use this fundamental formula to help understand that system a bit better. So frequency analysis, what it does, it calculates those resonant frequencies. It calculates that 1 hertz resonant frequency. It calculates the 15 hertz. It figures out all those resonant frequencies. Okay, and then I can use those. Let me go actually back to one of these. I can use those to make better design decisions, such as where I may want to place supports. If this was a circuit board, resonating, I may want to place a support right about here. It'd create a different resonant frequency here. So you can use these mode shapes from a frequency analysis to figure out where you want to fix things, where you want to restrain things, to try to remove some of these natural frequencies. Okay. It's a very useful tool for that, and then I'll kind of show that in the basketball hoop. Now, next what I'd like to talk about, some fundamentals behind this next one here on the list, linear dynamic. So to talk about this, another principle that we'll need to bring up here is called modal superposition. Maybe you've heard of it, maybe not. And the basic principle behind it, let me show you something that's sort of parallel to this topic. That doesn't fall directly in line with it, but is very closely parallel linked to this idea of modal superposition first, and then we'll talk a little bit more about it. So here what I'm showing you is this animation of the very simple elements drawing a complex shape. And these simple elements are these rotating circles. You see each one of these little vectors here rotates at a constant rate. If you focus on any one of these vectors with your eye, it's all a bunch of simple elements, and we're able to produce complex shapes from just adding together all these simple elements. So this is something called a Fourier series, but not to belabor it much, I just want to indicate to you here we can create shapes like this. You see this shape here, this function. If I add together enough of these vibration shapes, okay, these oscillations or these rotations, if I add together enough of these, I can approximate complex shapes with a bunch of these simple sinusoids, a bunch of these simple vibrations. So this is a technique that's used in our dynamic analysis tools, okay, called modal superposition. And what I'll show you here is I have this static deformation. It's a bit arbitrary. I've just put a load upward on the end and also a load downward in the middle to produce this kind of wonky shape. And if I look at some mode shapes, if I look at the first natural frequency, if I run a frequency analysis and get the first natural frequency, it looks something like this. You see I'm superimposing it a little bit onto the image that I had before of just the static deformation. I'm superimposing it. Okay, and here's the resonant frequency down here waving up and down. You see it doesn't match. That static deformation I produced, it doesn't match this mode, mode 1. Let's look at another mode though. What about mode 3? It looks kind of like, it looks similar to mode 3. Okay, you can see the original shape here in transparent in mode 3, but it doesn't match that one either. And if I just scale that one up, it won't really work. If I scale it up to be twice, it might match there, but then this one will be even lower. Okay, so it doesn't really match either of these modes perfectly, but what we can do is I can take mode 1 and mode 3 and add them together. Okay, and you can kind of see how this addition would work. You look in the end here. If I add mode 1 to mode 3, if I add these two displacements together, I'm going to get a displacement twice as big. Okay. But what about, let's take one more point in the middle here. Here's mode 1 again. Mode 1 looks like right about here it displaces upward by about the thickness. Okay. And if I look at mode 3, it displaces by downward by about 2 times the thickness. If I add together a +1 thickness, add that to -2 of the thickness, I get about -1 of the thickness. So you can see that this static deformation, this arbitrary static deformation that I have here, is really just a combination of modes, a combination of just adding together those sort of vibrations. Okay. And any deformation can potentially be looked at that way. So the basic idea behind modal superposition is, instead of solving the system this way, where these are our elements, all these little tiny elements, these are the elements, and we're going to solve 30,000 equations to get to the answer. No, instead the modes are our elements, and now we only have to solve maybe 20 equations depending on how many modes we want to incorporate. Okay, so this really speeds, it's a really elegant method that we use in linear dynamic to speed up the solution process and get to the result more quickly. So that's how linear dynamic does things. It's going to take the modes, the elements that we'd calculate from a frequency analysis, takes those elements and uses those to solve dynamic problems. Okay, and we'll show that in a little bit. Finally, nonlinear dynamic. What's this tool about? Nonlinear dynamic, it's a little bit more crude actually. It just solves the motion equation directly. Just does the number crunching. No elegant method here. It's just taking, your mass times your accelerations, your stiffness plus times your displacements, and, balancing that with any kind of external loads you're applying, and if you have any damping in the system. It's just balancing the motion equation. It's just solving that directly. Okay, so this can take a long time on complex systems, but I'll show an example of this as well later. So it's nonlinear dynamic in a nutshell. So again, sort of the summary here. The frequency analysis gives you the mode shapes and resonant frequencies. We can use those as elements as part of a linear dynamic solution, or we can completely do it a different way and just use nonlinear dynamic and run it more directly. It's more of the direct method. So next what I'd like to do is we're going to walk through a series of simulations at different levels on this basketball hoop. So the first one I'll start with is sort of a hand calculation. You see these animations here, but this one here I don't have moving up and down. This is because I'm going to run this as a static deflection problem. Basically what I'd like to solve for in this analysis is, first of all, the natural frequencies. I'd like to figure out what are the natural frequencies of this structure. Okay, does it vibrate at 3 hertz, 20 hertz, 50 hertz? And also displacements. Ultimately, I'd like to estimate the displacement, and then that leads to stresses and so on. But to keep the presentation short and concise, I'm going to mostly focus more on the natural frequency results, and those are the ones we'll be comparing. And then if you have questions on how we might estimate some displacements later on, then let me know, and I can address that. Okay, but to keep this again short and concise, we're going to mostly focus on resonant frequencies. So for this first problem, to be able to estimate it with like a hand calculation, consider that this system behaves like a spring mass system. Okay, the mass is my weight hanging on the end of here, and the spring is the bending stiffness of this basketball hoop. And if I can look at it this way, I can apply simple equations like the one we showed before, where the resonant frequency is going to be equal to the stiffness divided by the mass, and so on, the square root and so on of that. Now, really, in order to figure out the stiffness of this, I just need to figure out what is the displacement. How much does this thing bend downward when I put my weight on it? Okay, and then I could derive the stiffness, and I know how much I weigh, so we can just plug in those numbers. So really, the equation boils down more to something simply like this. If I just take the coefficient of gravity if I'm on Earth and divide by the displacement, take the square root and figure that out, and that'll give me the resonant frequency without me having to even run a resonant frequency study. So let me show you basically just setting up a static study to figure out the first resonant frequency of this. Okay. So here in the SOLIDWORKS environment, I'm going to figure out the resonant frequency of this using a static analysis. Part of Sim Standard, or if you have SOLIDWORKS Premium or just Sim Standard, you can use those tools to do some very basic vibration calculations. So I'll run a static analysis. I'm going to put a material on here. I'll make this thing out of steel. I'll fix these back faces where this thing would be bolted. Turn on the face filter, make it easier to select faces as well. And over here, I'm going to place the load over here, but I can do this a variety of ways. And one of the ways I'm going to use more on the frequency analysis side is, instead of just putting a force on there, I'm going to put a mass on there, a distributed mass. And let's say 260 pounds, big guy hanging on the end of that. Okay, 260 pounds on there. But now that's going to be distributed onto this surface right dead center right now. So if he's hanging on the side or this side, I'm not really simulating that yet. Right dead center. I put this little split line on there. But now I also have to turn on gravity. So I'll go and enable gravity. So that way I'm accounting for both weight and also the weight of the basketball hoop as well. Incorporating both of those factors into there. Now I'll go ahead and mesh this. I'll break it up into simple bits and pieces here. Okay, I'm going to be using just a 0.5 element size just to keep things simple. And so it's a fairly coarse mesh. And we'll go ahead and run this and see what kind of results we get. And here I get a displacement of about 21 millimeter. Okay, and if I go ahead and punch that in, 9.81 divided by 0.0211, that's the displacement in meters. Okay, take the square root and also divide that by 2 pi, because this is in radians per second. Divided by 2 divided by 3.14159. Okay, according to this calculation, this rough hand calculation, that's only based on a static analysis, I'm figuring that this thing resonates at about 3.43 hertz. Okay, I haven't run any frequency studies on this, just based on a static analysis. That's kind of interesting. I can maybe make some resonance conclusions about that. About 3.4 hertz, 3.4 oscillations a second. So let's see how that jives up if I do actually move ahead with some of these other studies. Okay, so right now I estimated 3.4 hertz is the resonant frequency. Now here, a couple of assumptions I'm making here. So I'm assuming that this is undamped. This is an undamped system. And what about if I exclude the weight? You know, after I release this thing, you know, I pull down on it and then I release it and then it oscillates. What's that resonant frequency? I'm not really accounting for that. Okay, I was accounting for the weighted resonant frequency, and then we can see a little more later what I can do if I get rid of these assumptions. So next, what I'd like to do, let's run a frequency study next, and then see what this tells us. Be a little more direct than me doing that hand calculation. So a frequency study, I'm going to reuse a lot of this setup that I already did, okay, for my frequency study. But basically, what I'll start with, I'm going to create a new study. And I'll run this as a frequency study this time. This is part of that Simulation Professional toolkit, SimPro. And what I can do is, if I go back to that static study I set up a moment ago, and I can copy over a lot of this stuff, my material, my mesh, pretty much all this stuff, I can drag and drop it right into my frequency study. So now my frequency study is pretty much set up and ready to go. So here was one of the big reasons I did it as a mass instead of a force, though. If I did that load as a force here, the frequency study wouldn't account for it as a mass that's also moving up and down with the system, and it's going to way overestimate the natural frequency. Okay, so it's important that I did that. I included a mass here, so the mass, the resonant frequency has to account for that, having to swing that mass up and down if I'm really holding on to this thing for some period of time. So now let me go ahead and run this frequency study as is. Okay, and it lets me know, hey, the frequency calculation, I can't do it with loads and use the iterative solver. And it gives me specific instruction. Change to the sparse solver. Okay. So if I go into the study properties, here's where I can go to change it over to the direct sparse solvers. I always use the Intel direct sparse. It's usually a little faster than the direct sparse, a little more optimized. Okay, so now I'll go ahead and run it. And what this tells me is, it says that first natural frequency, if I go and animate the thing, saying it's swinging, picture it swinging my mass up and down, that 260 pounds, swinging that up and down. Now this is of course exaggerated, but you can see up here the resonant frequency it came up with. It's saying it happens at about roughly 3.5 hertz, 347, in that ballpark. But in addition to that, I can also look at some other mode shapes as well, ones that hand calculation would have been a little trickier for it to provide me with. Maybe the side mode here. It's one that's going left and right. Now I don't expect this one to come into play because my load is primarily vertical. Okay, another mode here that kind of wobbles in and out. Okay, this one happens at 10 hertz supposedly, and again, maybe this one might come into play a little bit, but not as much as mode 1. What about this fourth one though? If I animate this fourth mode, would this one come into play? This is like a twisting mode. This one would come into play if I hadn't been hanging right in the center. If I had been offset a little bit to the right or left, then I'd see that I'd have to use, picture doing that modal superposition. I'd have to add quite a bit of this mode to get to the right answer. Okay, mode 4 would be pretty important. Okay, so it looks like mode 1 and possibly mode 4 are two very key ones here. So to summarize then, when I ran a frequency study, I got the first mode very close to that hand calculation. Okay, almost identical. Okay, 3.48 versus 3.44. But in addition to that, I'm able to calculate additional modes that would have been a little more challenging to come up with based on that hand calculation. I would have had to put some sort of torsional load on this thing to try to estimate what this mode might be. Okay, and it came up with 61.6 hertz for that mode 4, which might be important if my load's a little bit offset one way or the other. Now this still assumes that this is undamped. Okay, I don't have any damping on here, and that we have separate studies for hanging and releasing. So if I were to take that mass off of there, these frequencies are going to be way different. You know, instead of 3 hertz, if I take my mass off there and let this thing go, maybe this 3 hertz bumps up to like 50 hertz or something. Okay, because my mass is quite a bit compared to the mass of the hoop. All right, so next what I'd like to do, let's talk about running a dynamic study now. Okay. So for this one, let's go back here. If I want to run a full linear dynamic study on this, I'm going to set up another study. This time I'm going to select linear dynamic. Okay, and this is now I'm in the simulation premium package here. And there's several different types of linear dynamic studies, but what I'll be showing in this webinar is just this first option, modal time history. And what I can do with this is I'm going to be using those same frequency results as my elements in this study to calculate actual displacements. I want to figure out what are the true displacements that I get when I jump up, grab onto this, and ride it down and up, okay, as it oscillates. So I'm going to, once again, copy a lot of the setup I already did. Okay, that same material, fixture, okay, whatever I can copy, I'll bring it over into my dynamic study. And you'll see most of that stuff does copy, except for the gravity, for example. You don't see the gravity transfers over here. The way I need to manage this in a linear dynamic study, since I don't have access to things like gravity, is I will need to apply this both as a mass, and I'll have to say that mass exerts a force onto this face as well, through the use of gravity, essentially. But I'll have to emulate that gravity using a force. And I'll place that force on this face, same face where I put the mass. And I'll tell this force to go in a selected direction, point it downward. Use 260 pounds. And the way in which I'll apply that force, I'll say that the study begins as soon as I grab onto this and I drop. You know, I start dropping and it starts bending this. So I'm going to go in here and enter a curve that describes at 0 seconds this force is on there. It is 100%. That's what this multiplier means. That force is going to be 1. It's on. And at 1 second, that force is still going to be on. Okay, so I'm instantaneously applying the load, and that load's going to be on throughout the entire duration of the study. Now, in actuality, the way the force is truly applied, picture if you are hanging onto something that bends and flexes quite a bit, your actual body weight will contribute. You'll feel on your hands a bigger force when you're in the bottom part of that oscillation, because it starts to try to accelerate you back upward. So to assume this is a constant force isn't exactly right, but I think for the purposes of this presentation it should be close enough. But if you did need to put in that more precise force equation, you can enter that in, copy paste from Excel into here if needed. Alright, so I'll apply that force along with the mass itself of it. And in addition to this, I'll add some damping. Okay, if I edit this damping, I'll say that this thing loses energy at about a rate of, in the ballpark of 2%. It's not precise for me to call, I shouldn't call this a percentage per se, but for very low damping values, it behaves very, very, very much like a percentage. Okay, so it's sort of like it's going to lose 2% per oscillation. And finally, what I'll do is, if I go to my study properties, I'll change the dynamic options here. I can tell it to run the full 1 second, and I'm expecting to see about 3 oscillations. If it's 3 hertz, I'm expecting to see about 3 oscillations in that 1 second. That might be enough for just to make some quick judgments. And I'll speed it up further by just bumping this time increment up a little bit. I'll just solve for about 50 steps. Okay, but this is a number. If you do want to scale this number to make sure that you are accounting for whatever the highest natural frequency that you want to account for in the study, you need to make sure this number is small enough that it's able to capture that. Alright, so with that, we'll go ahead and one other thing I'll change as well. If I go under my result options, For this first study, I don't care about the calculation of stresses, or I'm just going to look at the calculation of displacements. Now there's another option down here. You see it's grayed out. I can select modes, and this is kind of important for me to show you here in a moment. It's grayed out though. I can't select modes right now, but let me go ahead and show you what this is about. I'm going to go ahead and click OK to this. And first what I'm going to do the first phase of my dynamic study. I'm going to tell it to run the frequency study. Okay, and this is going to run the same study that I ran before, a frequency study, and calculate resonant frequencies. And I can look at the table of resonant frequencies that it came up with. There's that 3.48 hertz again, and a bunch of the other ones. There's that 61.5 hertz again. That's the mode 4. Okay, and I can animate those just the same. But now these are the elements. Those frequency results now become the elements of the dynamic study I'm about to run. If I go to my result options, I can actually go under selected modes and turn on and off different elements. I could say, you know what, this mode doesn't contribute much, or these modes don't contribute much to the answer, so I can speed things up a little bit and just neglect them. I can kind of tell which mode is going to contribute the most. The one that has the most participation in the Y direction here, which is this one here, 0.96 in the Y, whereas these other ones are E minus 7, tiny numbers. Okay, so this mode 1 looks like it's the most important in that Y direction, so I do want to make sure I keep that one turned on. So basically this analysis is going to take these elements and tell us how much of mode 1, how much of mode 2, how much of mode 4, and so on are going to contribute to the full result. Now in this case I'll just tell it, go ahead and use all the modes. And I'll go ahead and run the actual dynamic study. So it takes those 15 modes. You see that's sort of the degrees of freedom in this problem, is the actual number of modes. And it's running those 50 steps. It's like running 50 analyses. So it still does take a few seconds. And once it's done running, now I can see the dynamic behavior. Let's go ahead and see how those modes oscillate. If I go and animate the result, I'll let the animation play through once, and then I'll kind of speed it up here. Oh, a little slower. How about right there? You see that 2% damping isn't much. I can barely see it's losing energy. Okay, as it repeats this animation over again, you can see the time up here, 0 to 1 second, as it repeats over and over again. Okay, and let me go ahead and probe though. If I probe one of these end locations and graph that result, you can see, yep, it is losing a little bit of energy as it's going along. Okay, very slowly. That damping isn't significant. Okay. All right. Now, what if I wanted to release? What if I wanted to run a simulation where I release this thing and watch it fly upward and then oscillate? I'd have to do that as a separate study. I cannot turn on and off masses in the middle of my dynamic study. I could turn it off now and then remove it. I could remove it from the study and rerun it, and I'd see those higher frequency oscillations. And I've already done that, and here's kind of what that looks like. Here I'm applying a load and then releasing. See much faster vibrations. Okay. So to summarize, so here's our linear dynamics study. We're using those same frequencies. So you see the frequencies aren't any different, right? It's really, we're just piggybacking on the results we got from this to run this study. Here's those same frequencies, but and you can see the results here of the one I just ran, but also one if I wanted to do a release and see those vibrations, and you see how quickly the energy is lost in those higher frequencies. That 2% does quite a bit there. Okay, but these have to be two separate studies. Okay, I had to run this as one study, separate study to look at the release because of the fact that I cannot turn off mass in the middle of a study. The last study I'll run is going to be a nonlinear dynamic study, a more direct study. Let's show you what this one looks like. So once again, I'll set up one more study on this. This time I'm going to select nonlinear, and here dynamic. Okay, we have nonlinear static and nonlinear dynamic. And once again, it's pretty much going to be a lot of the similar setup. Okay, same material, same fixtures, all that kind of stuff. Let's see if I can copy over some of that stuff though. Like, can I copy the fixture? Okay, and can I copy the distributed mass? Okay, you'll see what I'm able to copy and what doesn't quite transfer over very well. Okay. So I couldn't copy that distributed mass. Okay. The option for distributed net mass is not available in nonlinear dynamic. And actually, the way I'll do this, I won't use a distributed mass after all. I should do this more directly. In other words, I should do it like I should model the mass. So here, I've modeled a hunk of material here, and I've signed a hunk of a block here rather, and I've signed a material to it such that it weighs 260 pounds. And I'm going to basically just, in the nonlinear dynamics study, just turn on gravity and let it fall and see what happens. So I'll do another new study, or I could copy that configuration over, I suppose. Okay. Assign materials just like we did before. Assign my fixtures. So quick to do that, I might as well just do them here. And what's going to be new here? Gravity, that's standard. Okay. Something you do have to be careful with in these studies when you enable things like gravity is you do have to make sure you don't do it linear, do it as a curve. So make sure you're turning on gravity in the beginning so it doesn't try to scale gravity up. But what I usually do to help convergence is I will have a small period of time in the beginning where gravity is off and then it turns on. Okay, so maybe at 0 seconds gravity's off, at 0.1 seconds it's on, and then don't need that row. Let's see here, at 1 second it'll continue to be on. Yeah, strange why I can't delete that row for some reason. But anyway, so at 0 seconds it's going to be off, at 0.1 it's going to be on, at 1 second it'll still be on. So I do like to have a little period where it just scales up, just a small period where, just to help with convergence so it doesn't instantly bump into that surface at time equals 0 and things start oscillating wildly. Okay, so we're going to ease into it and then run it that way for nonlinear dynamic. So that's gravity. I've got, now here though I do have to be careful. I do have to assign a special material, one that has a density that will give me the right mass. Okay, so I've created a material that does just that. Okay, it's got this mass density that's scaled way up, so it'll weigh 260 pounds. And I can verify in the simulation that that's going to be the mass of it. If I go to my mass properties in here, it tells me 118 kilograms, and I guess convert that. There it is, 260 pounds, plus the weight of the hoop and all that, I think, is incorporated in that too. Or actually here, didn't quite scale it exactly right, but I think you get the picture. Let's see, and then the mesh. I'll create the somewhat coarse elements, kind of like before. Can be a bit wasteful over here. I might even want to coarsen the mesh up on this mass, since really this could be comprised of just a few elements. Okay, but just to get, I won't be running this study from the beginning anyway, so I'll, because this one takes too long to run. Then damping. For damping, we're going to handle it with alpha and beta coefficients. Okay, and these are just multipliers that'll multiply by the mass matrix and the stiffness matrix. A very short, elegant way of doing this, but it doesn't perfectly match reality, and coming up with these coefficients may take some experimentation. Okay, what I'll do, I'll key in a couple of coefficients that gave me pretty stable results here, and they gave me very close to 2% damping. All right, and then another thing I'll do is if I go to the study properties, here's where I can go to set those same time steps. For this type of study though, since I do plan releasing the load, pushing the load off of here, I may want to make these time steps a bit smaller. In the nonlinear dynamic study, this is the critical step. You might think it uses this to some extent. No, it's really, nonlinear static uses this guy. Nonlinear dynamic, this is going to be your critical time step you need to key in there. Okay. Use an Intel Direct Sparse Solver, and not really skipping anything. I think that's all the key steps I would do for setting up this type of study. Maybe turn off the show results as well, intermediate results while it's running. But in principle, that's how it's set up. Oh yes, of course, in the contact. Okay, it's also my notes here. Need to make sure that these two bodies don't go through each other, so I'll set up a contact set that will take that contact into account. Make sure that these faces here. Okay. And I've specifically modeled these rounds here to help smooth the contact region out a bit. I'll say that stays in contact with that. Okay, or that's going to make contact with that. I've got a little angle on here so it stays on top of it and doesn't slide off. And to keep it from sliding left and right, you might also add some stabilizing fixtures onto this body. Something that would just tell this, like this node here, you're not able to move left and right. Okay, just to keep it stable from flopping around. Okay. So those are all the key elements. I think one other thing I would add is something that would push this thing off of here so I can get the animation I was showing you in that PowerPoint. I might add a force onto here that only comes into play at about 0.5 seconds and just pops this thing off of there, and I can see what happens when this thing is released, how this thing jogs upward and starts vibrating. But if I were to run this study, it could take hours, and it does. It takes hours to run this compared to a few seconds that it took to run that linear dynamics study. The linear dynamics study modal superposition method, very elegant, works very well when applicable. Works well for linear problems where you're not changing things in the middle, like removing masses. Okay, but if you do need to have things changing in the middle of things, we might have to use the more direct method, nonlinear dynamic, and it can take a lot longer to run. So when I ran this study, I got results. Let me go to one of the result plots. Okay, you see the setup pretty similar to what I just kind of walked you through there. I'll start with a displacement plot. Okay, so it shows the displacement. If I go to try to animate this, it has to filter through a lot of those results too. Okay, so here I've got 1,000 frames worth of an animation. Let me filter this down just to the first few frames, perhaps. As this thing falls into place, bounces up once, and that's probably all the frames I've animated here, just for simplicity, just for speed, I guess. Okay, bouncing around there. So, and I can create those same kind of plots and graphics to summarize then. Okay, so here's what I could do with this if I created a graph similar to the way I did in the linear dynamics study. Here's the kind of graph I get. It goes down and up, down and up. It doesn't tell me what the resonant frequency is directly. If my goal was to figure out resonant frequency using a nonlinear dynamics study, you can do it, but you'll have to do it a bit manually. You'll create a plot like this, and then you'll look at the distance between these troughs, or the distance between the peaks, and you're going to calculate the frequency based on those. You're going to have to do a little hand calculation there based on this time to figure out that frequency. And it seems to be about 3.5 hertz. You know, you see in the period of 1 second, it goes down and up. 1, 2, 3.5. Seems to match with what we were seeing before. Do we provide an FFT option to get frequencies in nonlinear? No, it's not built in. Okay, I can provide you with a spreadsheet that maybe helps with it a little bit, and there's also little programs you can download too. VibrationData.com has a little DFT program that'll help you take the Fourier transform. But no, it's not directly provided in nonlinear dynamic. So here you can see those vibrations and then the release, and you can see when I release it, very high frequency vibrations because I removed the mass, of course. Here's the full-blown animation. Oh no, pardon me. This is a different animation. This is an animation showing what if I start this thing higher up. If I start at 6 inches off the surface. So in other words, I jump a little extra high, 6 inches higher than the hoop, and then I come down onto it. You see it creates even larger displacements, very large stresses too. And you see that contact it makes as it releases too. Goes up, high frequency vibration, hit it, more high frequency vibration. Okay. But here, this animation I'm showing you here is more in line with what I just ran, okay, or what I just showed the setup for. Okay, I turned on that, I stabilized this thing, had it be initially starting at that position and comes down and up. So I can derive, if I do that hand calculation, I can derive the natural frequency, 3.51 hertz. Good luck driving the fourth frequency that I was looking at from these other ones. I don't really have a twisting mode on here, so I'd have to impact it, create that, and excite that twisting mode, and then maybe I can do that same kind of manual FFT on there per se, or a direct one, and I might be able to drive that one. But this study doesn't show me that. Okay, the way I set it up currently. All right, so I guess in summary, we talked about the using simulation standard to estimate first resonant frequency. Then we used Simulation Pro to come up with other resonant frequencies. We took the results of SimPro study and plugged it into a dynamic study to calculate displacements, calculate actual, and stresses can come from that, of course. Then we also ran another version of a direct study. We did a nonlinear dynamic where I actually modeled the mass and dropped the mass on there, and we could see what happens during the loaded period and also the release period, both of those simultaneously. Okay. We also talked about some fundamentals behind this, behind the scenes, calculating resonant frequencies and modal superposition, the method used by linear dynamic. And we ran this same study, sort of 4 different ways to estimate those resonant frequencies and displacements. So if you'd like to attend any of our training classes, we offer a 4-day bundle, okay, that talks about the static analysis. This is like analysis basics. Talks about meshing and gravity and just simple load case scenarios. It's a 3-day class, and then a 1-day extension of that that's bundled with it talks about the frequency analysis, which is required to run dynamic studies. The dynamic class is a separate 2-day class, which we normally cover some frequency study in that class as well. So if you're already familiar with the basics here, you don't have to necessarily commit to all this. You might just be able to jump to the 2-day. And then on the nonlinear side, if you want to know more about running nonlinear dynamic studies, officially there's a lesson in this class that talks about nonlinear dynamic, but to talk about those convergence issues and stabilizing things, this is more of the topic of this class. Thank you all for attending this webinar. If you have any further questions, just shoot me an email.